What if an AI could be like a doctor for machines, but instead of a stethoscope, it just listens? It listens to their mechanical heartbeat, and it can actually tell when they're about to get sick. Well, today, we're going to dive into the incredible science behind AI that can actually hear machines breaking way before it ever happens. I mean, really, just think about that. What would that mean for you? No more sudden, catastrophic failures bringing production to a screeching halt. No more crazy expensive emergency repairs. Instead, you get this quiet little heads up, giving you plenty of time to fix things. And look, this isn't some far-off sci-fi dream. This is happening right now. It's the cutting edge of something called predictive maintenance. So the big question is, how on earth does it actually work?
Okay, so to get that critical early warning, we've got to start with a really cool idea. Every single machine has its own secret language. And you know how it speaks? Through vibrations.
Right. So as all those motors and bearings and gears are whirring away, they're vibrating constantly. But here's the thing. Those vibrations aren't just random noise. Not at all. They're actually a super rich, complex signal, a language that tells the story of that machine's health. A healthy machine, it's got this nice, steady, predictable rhythm. But as parts start to wear out, that rhythm changes. It starts to get a little off. It might develop a tiny stutter or a cough in its vibrations. And that's our clue. And that, right there, is the whole ballgame. That's the goal. We're trying to get away from what's called reactive maintenance. That crazy panic when something breaks and you're scrambling to fix it. We want to move to predictive maintenance, using data to basically see into the near future so we can schedule repairs all calm and collected way before disaster strikes. So, okay, we've got the goal. The question is, how in the world do we translate this crazy, complex language?
Yeah, well, it's not easy. Not by a long shot. These vibration signals, they're an absolute mess. They're filled with background noise, all these complicated patterns. The best way to think about it is like trying to hear one person whisper in the middle of a packed, roaring stadium. For a human, forget it. It's pretty much impossible. But for an advanced AI, this is the kind of challenge it was built for. And researchers are tackling this with two really fascinating approaches.
All right, let's look at the first strategy. We're going to call it the AI bake-off. And the idea is actually pretty simple, but it's super powerful. You just take a bunch of well-known, high-performing AI models, line them up, and basically make them compete to see which one is the best at translating these machine vibrations. So one researcher, Michi Chang, decided to explore this exact question. The thinking was, hey, we have these powerful AI models that are already crushing it in other fields like finance or translating human languages. Could we just, apply them to the mechanical world? The focus quickly landed on a whole family of models that are perfect for this kind of thing, for analyzing data that happens over time. They're called recurrent neural networks. So, in this bake-off, we had three main contestants. First up, you've got your basic RNN. It has a pretty simple memory for sequences. Think of it as having a short-term memory. Then you've got the LSTM. This one's more advanced. It has a really powerful long-term memory, which is crucial for spotting patterns that develop over a long, long time. And finally, there's the GRU. It's kind of like a more efficient, stripped-down version of the LSTM. So the big question was, which of these is going to be the best at understanding the long-term health of a machine? So, who won the bake-off? Well, the results were pretty darn clear. The more advanced models, the LSTM and the GRU, they totally came out on top. The research paper says they achieved a significantly lower mean absolute error, which is really just a fancy way of saying they made way, way fewer mistakes in their predictions. In fact, the LSTM hit an accuracy of 98.2%. I mean, that's a fantastic result. But is it the only way to tackle this problem? And that brings us to a totally different strategy. If the first approach was like an AI bake-off using recipes that we already know work, this second one is all about creating a brand new custom recipe completely from scratch, one that's designed for this one specific job. This is the really innovative path taken by another researcher, Pinchia Lin. The idea here wasn't to just grab an off-the-shelf model. Nope. The goal was to engineer a system from the ground up, one that's perfectly tailored to deal with the messy, noisy reality of machine vibrations. And to do it, they came up with this really clever two-step powerhouse of a method. And the logic behind this is just so smart and elegant. Step 1, clean the signal. It's that simple. Before you even let the AI touch the data, you use this special technique to just filter out all that junk, all the background noise. You isolate only the really important bits of the vibration. And then, step 2, you
You take that beautiful, clean signal and you feed it to a super translator, a state-of-the-art AI model called a transformer.
Okay, let's zoom in on that first step, this EMD thing. Seriously, the best way to think about it is like putting on the world's best pair of noise-canceling headphones, but for data. It takes that chaotic, messy vibration signal and just skillfully breaks it apart into its core pieces, its fundamental frequencies. The result? The machine's secret language becomes so much clearer, so much easier to understand. And then, once that signal is crystal clear, it gets sent over to a transformer. Now, you've almost definitely heard about transformers. They're the magic behind all those huge language models like ChatGPT. And the reason they're so good is that they are phenomenal at understanding context and seeing the big picture in long sequences of data. They don't just look at one vibration at a time. No, they see the whole sentence. They get how different parts relate to each other over time. And that makes them absolutely perfect for catching those super subtle, long-term signs of a machine wearing down. Okay, so we have our two main contenders. In one corner, we've got the bake-off, with proven champs like LSTM showing they're really, really good translators. And in the other corner, we have the new recipe, this custom-built two-step powerhouse. The question is, which one is better? It's time to look at the results. And wow, the results pretty much speak for themselves. Take a look at that first bar. That's the best model from our bake-off. It got a super respectable 98.2% accuracy. That's great. But now look at the second bar. That's our new recipe. By cleaning the signal first and then analyzing it with a transformer, well, that pushed the accuracy into a whole other league. Yeah, you're seeing that right. On one of the key datasets, this new recipe hit a staggering accuracy of 99.96%. I mean, that is just mind-bogglingly close to perfect. Think about it. That's the difference between being right almost all the time and being right every single time. This custom-built approach wasn't just a small step up. It was a massive breakthrough.
Okay, so an accuracy number that's basically 100%, that's not just an impressive number you see in a lab report. This has huge, profound implications for the real world. So let's talk about why this matters so much.
Well, for starters, you're talking about massive cost savings. Maintenance becomes predictable and way more efficient. Then there's the huge increase in safety. I mean, just imagine being able to prevent a critical failure in something like an airplane engine before it happens. This tech is also a giant leap toward creating factories that are truly autonomous and can basically maintain themselves. And the crazy thing is, it doesn't stop at factories. This same method could be used on literally anything that vibrates. We're talking bridges, buildings, even critical medical equipment. So this leaves us with a really fascinating thought to end on. We just watched an AI learn the hidden, secret language of a machine's physical health. If we can create this deep level of understanding, this brand new dialogue between us and the things we build, it makes you wonder, right? What other secret languages are just waiting out there to be translated? And what's the next thing we're going to ask our creations to tell us?